start. Hopefully this time it will go without any problem. Okay, so what we have done in the last class, we managed to derive the FRW metric. Okay, starting with the assumption the universe is homogeneous and isotropic, and the metric is again just to write down the metric. This is the metric that we have derived, and we need to write down the Einstein's equation, and the two Einstein's equations that we wrote, okay, was that. So was these two equations. This is the one equation, and the other equation was this, right? And we also argued that this equation, the second equation, if rho plus 3p is positive, a double dot negative, it actually gives you the fact that whatever be the component of the universe, but as long as rho plus 3p is positive at the finite past in the universe, maximum it can go to the age of 1 by h naught. Other than that, greater than, the less than equal to 1 by h naught in the finite past in the universe, we always have a time when a goes to 0. So there is a singularity in the universe, right? And that singularity we cannot avoid. Right? Okay, so that is the fact, fine. And with that, we'll now try to see that what kind of other dynamics that we can get from this FRW metric. Fine. Okay, so what you can do, I am not doing all the algebra, but you can actually use these two equations. You can actually use these two equations, and we can derive an equation, just a couple of 1 or 2 lines. Okay, I don't want to derive that equation like that thing. I am sure all of you can do. You can get an equation which is something like that. Okay, so this equation you can get. Fine. Now, as you can see, this rho is the energy density, and this is a cube is sort of a volume. Fine. So this is sort of a total energy you can talk about. Fine. This is basically volume. So this equation looks like some sort of a equation. Okay, sorry, d of this. So this is looks like some du plus pdv kind of equation. Right? But just keep in mind that it looks like that, but exactly this is not the total energy in the universe. In GR, we cannot define in a sense a energy of a universe or energy of a gravitating object, okay, or gravitating system. But it just looks like that, this equation, just to keep in mind. And this equation you can also get because we write down the T nu mu form. If you remember, we write down the T nu mu form was a diagonal rho minus p minus p minus p. And if you this T nu mu, and we know that the Einstein's equation, the G nu mu has the Bianchi identity. Okay, so that we know, and that's why the T nu mu also has this sort of a conservation sign. So I can write this equal to 0. Fine. So this equation can also one can get from this equation. Right? So this can also give you this equation. Otherwise, with these two equations, you can also derive this equation. Okay. Now, the fact is that why this equation is important, because as long as I give you some p, which is a function of rho. So if I give you p as a function of rho, which I call the equation of state, then I can integrate this equation to get the rho. Okay, because the p will be function of rho. So then this equation is just a function of rho and a cube, and I can integrate this equation to write down a as a function of, rho as a function of a. Okay, once I have this rho as a function of a, I can put back that rho as a function of a over here, and then this is the first order differential equation. I can integrate this equation to get a to solve for a. Right? So that's why this equation sometimes is much more handy than this equation. This is the second order equation. But usually in most of the time in cosmology, we'll use this equation and this equation together with some equation of state giving P equal to F rho, and then we can solve this system. So that is usually what we do. Okay. It seems that there is some question. So can you hear me, students?
Yes, sir. Sorry for interrupting you, sir. The left-hand side 1A will be missing. It's in
Where?
acceleration, in
Just
acceleration equation, I think.
uh, what? Oh, yeah. This is a dot a double dot by a. Thank you very much. Okay, thank you. Okay, so now on we just use this equation and this equation to solve the system. Okay. Now there is another thing, and together with the equation of state. Okay, that P equal to F rho that we use. Fine. Okay, so now there is another thing one can do, which is important actually, which is that let's say I know that this equation is the first equation. That equation is given by 8 by G by 3 rho. I can take that side. Okay, so I can write this as K by A square equal to, I can take common 8 by G by 3. Then I have rho over here, and then I have 3 by 8 by G, and this is A dot square by A square. Okay, and I know that this term is basically H square because I define H is A dot by A, right? So what I have over here is 8 pi G by 3 rho minus 3H square by 8 by G. Okay, so that I have. Right? Now, as you can see that this equation, this 3H square by 8 by G, if you just look at it, this also has a dimension of the same dimension of the, right? So that has the same dimension of the, okay. So this quantity I can define at any point in the evolution of the universe. I can define a quantity which is 3H square by 8 by G. At any point I know H, let's say, and then I can define this quantity. And I call this quantity as rho C. Okay, some sort of a critical energy density. Okay, I just explain why I call it critical, because now if you can see that if I write down this equation, which is K by A square, so this equation is now 8 by G by 3 rho minus rho critical. Right? And now if you can it's straightforward see that if rho equal to rho critical, then K equal to 0. So at any point in the history of the universe, if rho equal to rho C, then the K is 0. And K is a constant. So if it is 0 at any point of the universe, it is 0 at every space, every time in the universe, right? Because K is a constant. Okay, so it remains a constant. Okay. So if I can at any point, if I can measure this rho, I can measure the H, and from H I know what is rho C. So, and if I see that these two are equal, then I can get an idea that what is the K. And if these two are roughly equal, then I can say the universe is flat. Okay? Because K is constant, if I can measure it at any point, that value still remains at any other time in the universe. Right? So what I get from here, that if rho equal to rho C, this K is basically 0. And if rho greater than rho C, fine, then K is positive, and we have the positive value, which is K equal to +1. Or if rho less than rho C, we have K equal to -1. Right? So I can get a flat, a closed, or an open. That we can get. Okay, so this rho C, that's why I call it critical energy density, because it gives a kind of a critical value. And if the total energy density of the universe is equal to that critical value, we can get a flat universe. So that actually represents that the universe is a flat universe. Right? Okay, so that's the significance of this rho C, or this criticalness of this critical energy density. Fine. Now, these are all dimensionful quantity, as you can see. Rho is a dimension of energy density, rho C is a dimension of density. So we can define a dimensionless quantity, and from now on we use that dimensionless quantity. So we define kind of a dimensionless density parameter. Okay, and we define this density parameter of rho is equal to rho by rho c. Okay, so this is a dimensionless quantity. Okay, and just from here, then you can see if rho greater than rho equal to rho c, then omega is 1. If rho greater than rho c, then omega is greater than 1. And if rho less than rho c, then omega is less than 1. Fine. So whatever we have over here, in this case, we have this is equal to 1. This case, we have this is greater than 1. And this case, we have this is less than 1. In terms of this dimensionless density. Okay. And we'll very shortly, we'll see that we'll write everything in terms of this dimensionless energy parameter. Actually, in the observations, what we actually see is basically this quantity. We actually measure this quantity and the dimensionless density parameter for different component of the universe, whether universe is non-relativistic matter or radiation or dark energy or whatever. So we have what we actually know from observations, that we have roughly three kind of matter that we have in the universe. Okay. And it all depends upon what is their equation of state. As I said, that the equation of state is basically given by P equal to F rho. More or less, you can define a parameter there, the equation of state parameter, omega, and we write it as P by rho. Okay, so that is the equation of state parameter we define, fine. And there are three sort of a, roughly in the universe, what we know, that there's three sort of a matter that we can have. In one case, this omega, which is P by rho, which is basically 0. Okay. Now, what is this? Now you can see the rho is the energy density, basically the number, total number of particles into mc square. Right? This is the, for a single particle, the energy density, rest energy density is mc square. So you that into the number. So this actually goes like mc square. P pressure is related roughly to the velocity or the kinetic energy, so it goes like v square, fine. Mv square, half mv square, fine. So if v is very, very smaller than c, then this term, this p, I can ignore in terms of rho, fine. So it is basically roughly 0. So this is basically what is called the non-relativistic matter. Right? So those things in the universe which are moving much, much, much slower than the velocity. And all the matter distribution that we can see in the universe, whether this is planets, stars, galaxies, cluster of galaxies, super clusters, all the whole everything, that we put in this category, this non-relativistic matter. Right? Then there can be relativistic, I mean, like radiation that we can have, like most of this contribution comes from this photon, the CMB photons. And for that, this P, which is P by rho, this is roughly 1/3. Okay, so this is basically the relativistic matter. Okay. And then there are another third kind of thing that we call dark energy, and we'll discuss more in our dark energy lecture. But one of the most simplest dark energy behavior or dark energy candidate we have, which is P by rho, which is basically -1. Okay. We call it a cosmological constant. Okay. So we believe that universe mostly, whatever we have in the universe, they mostly can be categorized in these two kind of matter. One is the non-relativistic matter, where essentially the P is 0 or the W is 0. One is the relativistic matter, mostly in the radiation in the universe, that is P equal to 1/3 rho. And then there can be cosmological constant where P equal to -rho. Okay. Okay. So now once I have this thing, okay, once I have this thing, then I can use this thing, this equation that already I wrote you. I can use this equation that D of rho a cube plus D of D a cube equal to 0. I can use this equation and then I can put all these things. I can put P equal to 0, I can put P equal to 1/3 rho, or I can put P equal to -rho. Okay. So just do a little bit calculation. It's again very, very simple calculation. So if I do it, so for first case, non-relativistic, okay, when basically P is 0, okay, so it just this term vanishes. Then what I have from here is the energy density, the rest energy density. This just goes as -3. And as you can, this you can expect because there is nothing except this, all these non-relativistic particles there. So as the universe expands, the number density, so the energy density depend upon the total number, okay, into mc square. And as the universe expands, you take a box size of a cube, it actually expands, so the volume decreases as 1 by a cube, so the number density goes as 1 by. So that's the way the energy density time. Okay, so that is there. Then if I have the relativistic case, okay, matter, relativistic matter, which gives you P equal to 1/3 rho. Okay, and for this case, if you just quickly this, you put 1/3 rho and do a rearranging and do the integration, then you see that this goes like a to the power -4. Okay, and that also you can understand because now it's relativistic. So the energy goes like h nu, and we know that as the universe expands, you already show the nu, the frequency goes like 1 by a. So for the energy, it's actually individual particles, it goes like 1 by a. And again, the number density as it is go by 1 by a cube. So then overall the energy density falls like 1 by a. Okay. And then the thirdly, you have a cosmological constant where P equal to minus rho. And if you put P equal to minus rho, you do this a little bit algebra, you can show, and then integrate, you can show this rho is basically constant. And that's why it's called a cosmological constant. The constant, it remains same as the universe expands, right? So there is no change in this thing. Okay. So these are the three behavior that we can have in the universe, right? So I should write, let's say I just write as M. I can write this as R, and I can write this as rho. Okay, so that's the matter. In a sense, we call it non-relativistic matter, radiation. Right? Now, as you can see, these are all proportionality. So there is a proportionality constant coming over here, and we can put this proportionality constant like I say that like at present the scale factor is 1. So I can say that what the value of rho m at present is rho m naught, and then this is 1. So I can put this proportionality constant as rho m naught. Right? So I can have here a rho m. So I can put it equal to, and I put a rho m naught over here. I can put it equal to, I can put a rho 1 naught over here. And this is constant, so this remains constant. Okay, so that is the constant. So these are the value of rho n at present, fine. And as I said that I always assume a naught equal to 1. So that is my initial assumption. So that is the thing. Once I have this kind of thing, then I can actually relate it with this thing, with this density parameter, As you can see, this any rho is basically for that I can define a density parameter, and then that is related to rho c. Now, just to tell you that this rho c that I define as 3h square by 8 pi g. Now, what is its present day value? So for the present day value, I can put it 0. I can put it 0. I already told you what is the value of h naught roughly around present time, around 70 kilometers per second per mega per second. If I put all those values, put the value of Newton constant, all these things, it roughly comes out to be 10 to the power minus 29 gram per cc. Okay, so this is roughly the average density of the universe. Okay, so that is roughly this time. Fine. Now, so that what I wrote, again, I am just writing it. You just do a little calculation, and I am sure you can find it. So I write this as rho m naught a to the power minus 3. One can see that this very easily can be written as rho c naught into omega m naught. Omega m naught basically means omega m is basically rho m by rho c. Okay, and omega m naught is basically rho m naught by rho c. Okay, so density parameter is this, and any quantity, any matter contributed density will be that density divided by the critical density. Okay. So this can be written like that. Okay, it's very easy. Just you can, I am sure you can write it. And similarly, this also can be written as rho c naught, omega naught, a to the power minus 4, and rho lambda is rho c naught. So this you can very easily write it, fine. And once you can write it, I can come to this equation a dot square by s square plus k K by A square. This is equal to, now there are three constituents of the universe. So I have rho m, I have rho r, I have rho lambda. Okay, I put all those things over here. So I have here this, I have here this, I have here this. Fine. I can take rho c naught over here. Okay, and as you can see, this is h square. So I can write down this as h square by h naught square. So there will be an h naught square over here. So I can write this term as h square by h naught square. I can divide this by h naught square. So I can write this by h naught square into a square. And then this is 8 pi g by 3 h naught square. There is a rho c naught. I can take common from everything. So I can write rho c naught take common. And then I have omega m naught a to the power minus 3 plus omega r naught a to the power minus 4 plus omega lambda naught. And as you can see, rho c naught, I already write rho c naught. Rho c naught is 3h naught square by 8 pi g. So if you put 3h, sorry, yeah, h naught square. So if you write 3h naught square by 8 pi g, these actually get cancelled. Okay. So finally, what I have is that, I define, this is my definition. I define k by h naught square is something, some rather than minus this as some sort of a density parameter that is there in the curvature. This is my definition. I can do it, fine. Then finally, if I do it, I get an equation, which is this. So I put this as minus, so if I put this as, this part as minus omega k by 1 by a square. I take it that side, so this becomes plus. And then finally, I get this equation is omega m naught to the power 3 omega r naught to the power 4 plus omega k naught to the power 2 plus omega naught. And as you can see that if I go at present, okay, then h, this becomes 1 because this becomes h naught square. So this becomes 1. A naught at present is 1. This is 1. This is 1. This is 1. So what I get is like this plus this plus this plus omega k naught. So this is a constant equation. So in all this, so here you can see there are 5 parameters. One is the h naught square, and then this parameter, this parameter, this parameter, and this parameter. So the 5 parameters, but these 4 parameters are related by this. So if one parameter can be replaced by all the others. So this omega k naught I can replace as 1 minus this. Okay. So there are 3 parameters this, and then the parameter of h naught square. So this is the 4 parameter equation. And that is the most important equation that we use for any cosmology. So we use this equation to calculate all the geometrical quantities like different distances, different volumes, and other kind of things. If you go to linear perturbation also, then also there will be some background evolutions coming from here. So there also this equation will play a role. Okay, and so all the experiment now, our goal is to find out this parameter, this parameter, this parameter, and this h naught parameter. Okay. And if I know this parameter, I know what is the value of k naught also, omega k naught also. Okay. Now, what we actually now currently at present, what we know from different observation, already I said that h naught value. So for current observation, we already have some h naught, something very related to like this kind of value. Omega r naught is very small. It's roughly 10 to the power minus 4, 10 to the power minus 5, something that kind of value. And so that I can at any point, I can ignore this omega r naught. Omega m naught is roughly between 0.25 to 0.3. And omega lambda naught is roughly, if it is 0.25, then this is 0.75 to 0.7. And as you can see, if I have this sort of value and I put over here, you will see that the omega k naught is roughly very, very small. It's roughly. So what we get is inverse is sort of a flat. There is a 70% that I have in something called what is called cosmological constant. And then there is around 30% which is in the non-relativistic matter. And the contribution coming from the radiation today is very, very small. Okay? We can ignore that for the time being compared to this. Okay? So that is what we get. Okay? But what we also can see from here is that, okay, at this point, this omega naught is very small compared to this. Fine, this is around 0.3, 0.7, but this is around 10 to the minus 4, minus 5. So that is very small. But you see that it actually goes like a to the power minus 4. This goes like a to the power minus 3. This is a constant. This goes like a to the power minus 4 too. So as I go early from today, this increases much faster than the others. Okay, so let's compare matter and radiation. Even if today the matter is much, much bigger than the radiation, but as I go earlier, the radiation increases much faster than matter as I go earlier. So at some point, radiation will overtake matter. Okay, and the point when this actually happens, so that this thing and this thing become equal. After that, the radiation starts dominating. That epoch is called the matter radiation equality. So in the early time, there is the equality. There is the epoch, what is called the matter radiation equality, and it is very important. Okay, as you study the part of the universe, fine. As you go study part of the universe in the later lectures. So let's say that at some a equal to a equality, this happens, fine. And then you see that at that point, what you have is that a equality to the power minus 3 should be equal to radiation a equality to the power minus 4. Right? So what you get from here is basically that a equality is basically radiation by matter. Okay, so that you get. Right? If you, and as you can see that where it actually happens. Right? So you see that this is around 10 to the power minus 5. This is around 0.3. So you can see that this is 10 to the power minus 5. This is 10 to the power minus 1. You go 10 to the power minus 4, 10 to the power 4, some minus 4 something, and then by divided by 3. So it is around 10 to the power minus 5 or something. It's happening. Fine. It depends upon what kind of value you have. But whatever value you have, you can see that this happens quite early, okay, in the history of the universe, right? And that epoch is very important, very crucial, as you see that how the perturbations of different scales actually evolve, fine. And as you can see, so what we actually have that if A is smaller than the A equality, then radiation dominates. Okay, then radiation dominates. And if A is greater than A equality, then the matter dominates. Okay. So this is a very important epoch. It actually gives you the where from the radiation, we go from radiation dominated epoch to a matter dominated. Right? So that actually. Okay. There are some questions. Rahul Shah, among the 4 density parameters, are we able to measure all of them directly from the experiment, or is one of them inferred from the constant? Yeah, that I already explained, that you have these 4 parameters over here. There are 4 parameters over here. They are constrained by this equation. So what we actually do, this radiation, what is the amount of radiation? As I said, this amount of radiation is roughly in the photon, the CMB photon. It's a black body spectrum that we know with a temperature 2.7 degree Kelvin. So we can apply the Stefan Boltzmann law of E is sigma T to the power 4, and knowing T is 2.7 degree Kelvin, I can actually calculate what is the energy is there in the radiation. So that is omega unknown, right? That just comes from the CMB, and that value is, as I said, is around 10 to the power minus 5. The rest of the thing, omega m and omega lambda, because here I can replace omega k by all those things. So now here these other, so omega are not already I know. So then in this equation, there are other two parameters except H naught. The other two parameters are omega m naught and omega lambda naught. And this I will show that this you can actually measure. Means from the geometrical observation also you can measure. You can measure the distance in the universe, what is called luminosity distance or angular diameter distance. You can measure these distances, and then you can use different observations like supernova observations or DA observations. With that, you can actually get a constant of omega m naught and omega lambda. Okay. So, and also from CMB also you can not directly measure omega m naught. You can measure a combination of omega m naught and these H naughts. And then you can measure H naught from other things, means all those things, all those physics, and you can decouple all those things. So the fact is that we directly don't measure omega k naught. We measure all these three parameters, this parameter, this parameter, this parameter. All the four sum up to 1. So if I measure these three, then I know what will be the omega k naught. Omega k naught is 1 minus all those three. Right? And then knowing all those three, I can know what is omega k naught, and that actually gives that the current value of omega k naught is very, very close to 0. Okay. Fine. So that's this part. Okay. So what I will do, so what you can show is I will not solve everything. So just you can see that I have this equation. Fine. I know how this behaves. I know how this behaves. I know how this behaves. Fine. And as you can see, very early time, this dominates, then this dominates, and then this dominates. Fine. So, and you can solve the A in different epoch. Fine. If you saw also, because I know that this goes like a to the power minus 4. So if this dominates, I can ignore these two terms. I can put a to the power minus 4. And at that very early time, this part will be also dominating over this. So I can ignore this also. And so I can solve those things. And then I can do for other thing also, if we can assume the k equal to 0. So I'm just writing the solutions. I don't have the time to do all the solutions. So I'm writing the solutions, how roughly the scale factor behaves. So in the radiation dominated, okay, when rho r goes like a to the power minus 4, so it is dominated by radiation, then A basically goes like e to the power half. Okay, in the matter dominated, when universe is dominated by the matter, so that rho m is a to the power minus 3, then A goes as t to the power 2. Okay, and when you have cosmological dominated, so that rho lambda is roughly constant, then A is going like exponential sum t. Okay. Now you can see that there is a huge difference between these two and these, right? So if you calculate A dot for these two, you see that with time the A dot actually decreases, because as you can go, so you can see that as you calculate A dot, as because this power is less than 1, so A dot actually goes like 1 by t to the power some power, right? Same like here, okay? But here you can see that A dot also goes like exponential, right? So in these two cases, the velocity, okay, of the expansion of the universe or the expansion rate, this actually falls, but in this case, this actually increases. Okay, so if you draw a phase diagram, of the universe, right? So let's say this is A and this is A dot. Okay, but you actually see that initially there is a matter domination, there is a radiation domination, the A dot is decreasing, but then at some point A dot starting. Okay, so here at this point, what actually happens that rho lambda start dominating. Okay, so like the same thing that I have done over here, a equality when the matter and radiation equal, and I get this. You can do the same, that when the matter and the dark energy is equal, fine. So this and this is equal, and that equality you can say, that equality actually one can say that the A lambda, when the lambda starts dominating, right? This you can see, this is very easily, you can see this is actually omega lambda to the power 1/3. Okay. So this is actually, I don't say rho lambda, I say that this is a lambda basically. So here there is a turnover happens. We are somewhere around here. We are somewhere around. This is our A0, which is 1 that we have taken. The matter radiation equality may be around here, A equality. Okay. So all through the universe, the A dot means actually is falling, is actually decreasing, but around very close to present time, fine, we are around 14 billion years, or around, so redshift 0, as I said, around redshift 0.5, 0.6, you can actually see that actually this lambda term starts dominating, and there is a turnover in the universe. So here there is a change from the t to the power half to t to the power 2/3. So there is a change in A dot, right? But here this change is much more drastic. Okay, the change is that it's actually decreasing, but here there is a turnover point happening in the phase-phase diagram. So that is extremely sort of very, very interesting phenomenon is happening over here, and it has very drastic consequences. Okay, that we'll study in our dark energy part. So that is actually where the dark energy start coming. Okay. Okay, so all these are well and true. So I have another 15 minutes. In between, I define some useful quantities that you will use in your hands-on. First is the age of the universe. So I can define the age of the universe. So I can say my age of the universe is basically dt from 0 to, let's say, present day. 0 is where the A is actually 0, fine. That I said that there is always a time where the A becomes 0, right? Because the universe is decelerating. So that is my, let's say, 0, and T naught is the present day. But this I can write in a little bit different way, so that I can relate with the age than the expression that I wrote. So I know already I wrote you that there is a things called redshift that I can define, and this goes like 1 by A. Okay, this is basically the redshift that we have due to the expansion of the universe. And from here, dz dt is basically, you can see A dot by A square. This I can write as A dot by A into 1 by A. Now A dot by A, I know this is H. 1 by A is again 1 plus Z. So this is 1 plus Z. So I can write it over. So dt I can write as, so this is dz dt. Okay. So dt I can write as dz divided by, I can write dz divided by h into 1 plus z, fine, that I can write. And then there is a minus sign, but at 0, early time, we know that z is infinity. Today, z is 0, but there is a minus sign coming from here. So I can change the integration limit. So this becomes from the whatever, z equal to 0 today to z equal to infinity. Okay. So that's the thing that I can define as my age. So now this h I can write from here. I already said that that's why this is the most important quantity. I can write my age as h naught square root of all those things. 1 means a to the power minus 3. I can write 1 plus z cube, 1 plus z4, 1 plus z square, and so on and so forth. So if I know all these values, if I know h naught, I can actually calculate the age of the universe. Fine. So that we can do. Okay. So that is the way we can calculate the age of the universe. And this is roughly, as I said, at present, this is roughly 13.8 billion years. That is one thing, fine. The other thing that I can do is that two distances I can measure. One is the luminosity distance. And this is exactly what we do in our standard flat geometry. Only thing is that we have to rewrite things in terms of expanding universe. So if I know, you know that if I have a simple flat geometry, if I have a luminosity of any object, which says that is the energy per unit time, fine. and it is placed at a distance, some sort of distance, let's say r, fine, or d. Then I measure an apparent luminosity. So this is the luminosity. Okay, this is the apparent luminosity. What I do, I put it over here. It's at the center. I have a distance d. I want to measure the apparent luminosity. So the energy is actually sort of radiated uniformly across a sphere of radius d. So at a here, the apparent luminosity is the luminosity per unit area. Okay, and that is basically apparent luminosity is basically L by 4 pi d square. Okay, so if I know the luminosity of the object, let's say a bulb of 10 watt, 100 watt. If I know the apparent luminosity, if I measure the flux that is coming, okay, then I can get an idea about the distance. Okay, so that I can do. Okay, I will use the same thing, but in the expanding universe. Okay, so what is the distance in an expanding universe? So we already have this metric that is available for our, fine, and we already have this metric. Okay, let's say for the timing I am writing to make things faster, I write a sort of a flat metric, and I code the result for a non-flat metric. Okay, and I take the let's say the things are coming with a radially move coming photon is coming. And we have isotropic universe, so I can take any direction. All the directions are good. So if I do calculation in one direction, all the calculation is valid for any other direction. Right? So for photons, so I can actually ignore this term because the radially moving photon, theta phi is not changing. So I have this thing, but for photon, this is actually give you dt is plus minus, or dt by a is plus minus dr, fine. Or let's say, okay, I just keep it here. So let's say, so this is 1 by kr square, fine. Now, as you know that as the photons are coming, the dr is changing. So dr is actually decreasing. So I can take the negative sign, okay, because with time r is actually decreasing, fine. So I can ignore this plus sign. So I can take the negative sign, and I have this relation, and I can just integrate it. Let's say I am sitting at the coordinate location in my point. It is the origin. Okay, that is my origin, and some distance r. Let's say at some point r, things are coming, and let's say it is emitted at a time t1. So this is r and t1. Let's say I am sitting at origin, and this is emitted at t1. I am receiving at t0. Fine. So I have this thing. So I have to integrate that. Okay, the things are emitted at t1. It is received at t0. It is coming from distance r, received at a distance 0. Okay, so this I can do this integration. Fine. If I have a flat universe, so I can put k equal to 0. So I can have this is just r 0 dr, right, for the flat universe. But again, this term, as you can see, I already did this calculation that dz dt is h1 plus z, fine. Or here you can see dz dt is minus h1 by a. So dt by a is minus dz by h, fine. Because this is h, I take dt this side. So dt by a is dz by h, and there is a minus sign. So here I have this dt by a. I can write this as dz by h. Okay. There is a minus sign over here. There is a minus sign over. These two minus sign actually cancel each other. But now things are emitted at a redshift z. You received at today, which is redshift 0. And this is equal to minus r0 dr. But now, as you can see that I can change, so this minus just goes. But now I can change this integration limit both sides, fine. So what I ultimately get is 0 to r dr, which is the r physical that I have, fine. This is equal to what I have, integration 0 to z dz by hz. Okay. Now this again you can see that I can always do because my h is given over here. My h is given over here. Already my h is given over here. So I can put this expression of h in terms of z. I can put it over here with different value of omega m naught. I can calculate I can calculate this thing, right? Now, this is actually, as you can see, this is actually what we calculate the co-moving distance. But now the actual physical distance is the scale factor into the co-moving distance. Scale factor at present is A naught, and I put A naught equal to 1. So this I can call my physical distance, right? So what we have over here, that this D that I am putting over here, this D is basically this one. Okay, this part. Okay, fine, that is there. So this, for this part I can put this distance. Okay, but there are other effects also. Remember that what is L? L first of all is the luminosity. Okay, now the luminosity is basically depending upon the energy that is emitted. Energy is h nu, and whatever the nu that is emitted, when you receive that thing, is actually sort of redshifted by a 1 by a term. Right? So the energy that is emitted, the energy that you received is actually has a 1 by that redshifting term is there. Right? So that's why there is a redshifting term. This a term is there, which is some 1 plus z term that you have to take care of. Right? On the other hand, this L is the apparent luminosity. The apparent luminosity is basically the energy or unit area per unit time. So that thing that you receive per unit time, right? So the frequency that was emitting, if it is mu naught, so the per unit time, whatever the photons were emitting, what you are received is actually get changed. Okay, because the frequency gets changed. So there is another redshifting term coming from that frequency term also is there. Fine. So finally, so what we actually have now, what we'll actually have is now this apparent luminosity that we have. This is that actual luminosity we have. Then I have 4 pi, okay, whatever you have, this R physical that I have square. But at the same time, you have a 2 1 plus z factor comes. One is for E, another is for the frequency that is also per unit time is there. So that's why for the frequency also there is an extra 1 by z factor. So these things actually come. So altogether these are physical into 1 plus z, we call the luminosity distance. So the luminosity distance is then 1 plus z integration 0 z dz by. This H contains all the information about omega m naught, omega r naught, omega lambda naught, omega g naught, all the information it has. Okay, so this luminosity distance also has all those information. So if I can somehow measure this luminosity distance, I can actually also get some information about all those parameters that we have. Okay, in the geometry. Okay, so this thing is called the luminosity distance. So this is I can write A by 4 and BL is given by this. Okay. Question, let me see. Okay, any question from here? I'm going a little fast, I understand. But any question from here? Hello? Is there any question? Okay, so if not,
1 plus Z square.
Hello, your sound is actually not clear. Can you again tell me? Hello?
Sir, 1 plus Z square term in denominator, said that term.
Where from it comes?
Yes, sir.
Okay, so again, just come over here. I was saying. So this part is fine for the standard case, fine. Now this distance, I said the distance is now expanding universe is this distance, fine?
Yes, sir.
Okay, now come to this L, fine. What is the L? L is the luminosity. Luminosity, this part is basically energy per area, fine. This is the luminosity, fine. And when you have the apparent luminosity, this is the energy per area per unit time. Okay, so it is basically how much you are receiving the photon, flux of photon per unit time, fine. Now just see that there is an object in the very distant universe, fine. There is some object, the photons are emitted from there. But as the photons emitted and it comes to you, universe has expanded, fine. So when you receive that photon, the photon will get redshifted, fine. That I told you, okay, that we discussed, fine. That always this photon get redshifted, fine. And that's why the energy or the mu that is emitted, okay, that mu when you receive, that will be a smaller mu. The lambda becomes larger, fine. Okay, so that's why you get a, so that's why you get a factor. That's why you get a factor of 1 plus z, because 1 plus z is basically that redshifting term. Okay, that we wrote, fine. That whatever the del mu I can write 1 plus z. So this 1 plus z factor comes because this energy is redshifted, because the mu get redshifted. Okay. The second thing is that there is a unit time. That means from that object, when the photons are emitted, they are emitted some per unit time, right? So the frequency which they are emitted, when you receive them, okay, that get sort of redshifted, fine. So the frequency at which they are emitted and the frequency at which you received, that also get changed, fine. That also get elongated because of this redshifting, because the frequency that they emitted and the frequency that you get, they are different, fine. So that's why there is another 1 plus z factor comes from this part. Okay, one actually comes from this part, one actually comes from this part, and that's why there is a 2 1 plus z factor that is there, which gives you 1 plus z square. Is it clear?
Yes, sir. So, sir, there is no term counts for the area term, sir. Area is the length square. For area term, no.
No, that is the definition of the So okay, so that is the definition of the luminosity, fine. That area actually is this 4 pi d square, fine. That already is taken care of by this term, because now the area. So this area, this is the area, fine. So this area has now, instead of d square, I have this area which is d is basically r physical d, fine. So whatever the factor that is coming due to the expansion of the universe, this d square is now in standard static universe, this d is constant, fine. So 4 pi d square, the area is constant, fine. But now this actually is changing. So that is actually here. Okay. So that is actually here. So that you can see that this actually depends upon redshift or z, or that depends upon a, that means that depends upon. So the area factor is there. Okay. So the area factor is
okay,
there.
Sir. Okay. Understood, sir.
From here, and there is a factor coming from here, and there is a factor coming from here, 2 1 plus z factor. Okay, and this 2 1 plus z factor gives you a 1 plus z square factor. Is it okay?
Okay, sir. Understood.
Okay, thank you. Okay, so there is one last thing that I'll do, and then I'll stop. Maybe it takes some time, but okay, because okay. So that is what is called the angular diameter distance. So this is also the standard case that we know. The standard that we know, that if I have a length of the object, which is, let's say, L, fine, and let's say I have a flat space, I put this object at a distance d, fine, and then it gives you an angle. So the angle it subtends, that we know, is basically delta theta is basically L by d, fine. This we know. Okay, that if I have object of length L, I put at a distance d, then the area that it does, the angle that it subtends is basically L by d, fine. So if I can measure this theta, delta theta, what is the angle it subtends? If I know the actual length of this object L, then I can know what is the distance. Right? So that we can do. This is one way we can measure distance. Okay. Now this we can also use in cosmology, in FRW space-time. Only thing we need to keep in mind, again, the distance is changing due to the expansion of the universe. Right? So how we do that? Let's say I am here. Let's say you are here at some t naught, and you are located at the origin. So all your coordinates are 0. You are located at origin. And let's say there is an object which has a length L, okay, at some time t, when it's emitting some light or some signal it is emitting. It has a distance at which the r coordinates, fine, it will have, and let's say it subtends an area, an angle theta plus d theta. Okay, so what is this d theta? This d theta is this. So let's say this is your d theta, delta theta, or let's say call it delta. Okay, so this is the object that is there at a distance r. Fine, it has an angular separation delta theta. Okay, and it is at a time of te, it emitted some signal, and you are sitting in the origin, you receive that signal at t naught, and that angle that is subtends is delta theta. Fine. So what first I have to calculate? I have to calculate this L, fine, because if I know this L, then this distance that I call the angular diameter distance that I calculate from here itself, fine, this weaving distance. Now what is this L? Now this L is very easy to calculate. So you know that. So at this time, here it is at a constant time. It has a constant time, fine, with a constant phi, with a constant r. So what is this length basically? Because if I say that here there is a one space-time location, here there is a one space-time location, what is the distance of this space-time location? Given by the FRW metric. But the fact that in that FRW metric, my dt is constant. The dt is 0 because t is at some constant location. R is 0, means dr is 0 because r has a fixed location. Phi is also 0. Only thing is that changes is this is theta and this is theta plus delta. Fine. So what I have over here is basically you can see that that you have the distance that you have the L. So what is this metric? The metric is basically we know this is dt square minus a square t. So let's say flat inverse r square plus r square d theta square plus r square sine square theta d phi square. Right? But now at that point your dt is 0 because there is some current, some specific time location is there. dr is 0, d phi is 0. So only thing is this. So what we have is this length is basically scale factor that we have. Okay, that into this r into this d theta. Okay, what is this r? That r already I have calculated. That r is basically the co-moving distance from here to here, and then into the scale factor, the physical distance. That r already is given by this. That all already is given by this. Fine. So that is my r. Okay, and then scale factor at that time we know, and this d theta. Fine. So now from here I can calculate the angular diameter distance, this distance, which is L by del theta. Fine. So what is that? That L by d theta is basically at into this r, and this I call the angular diameter distance. So what I have for the angular diameter distance? The angular diameter distance is basically dA, usually called dA, capital D, angular diameter distance. Okay, this is equal to what I have. A is basically 1 by z into that r physical, which is basically 0 to z dz by a. Okay, so again, if I know h, omega m, omega naught, all those things, I can measure, I can calculate the angular diameter distance, I can measure the angular diameter distance, I get a constant of all those omega m naught, omega naught. And you can see easily the relation for this angular diameter distance and the relation of this luminosity distance. We have the luminosity distance relation. This, there is a relation between this angular diameter distance and the luminosity distance. So what we have, the angular diameter distance is always luminosity distance by 1 plus z square. This will always hold true. Okay, this is sometimes called the cosmic duality relation. So if the photons are all conserved, there is no in between the line of sight, there is no sort of absorption of photon or anything. In any geometry in the universe, this cosmic duality relation will always get valid. So your angular diameter distance will be always the luminosity distance by 1. And people try to find out whether there is any violation of this relation. Okay, they will try to do the measurement of luminosity distance, we will do the measurement of angular diameter distance and try to find out whether this relation is still valid or not. And till now, there is no, till now from observational data, you will have not found any violation of this cosmic duality relation. Okay? So that is the angular diameter distance. When you do the dark energy, we'll see that how one can measure this luminosity distance, how one can measure this angular diameter distance, and from these two things, how one can actually get to know the dark energy, okay? That the existence of dark energy. Okay? So I stop over here. There is only half an hour left for the hands-on. If you have some quick question, you can ask me, okay? And then Manavendra can go further. Why these distances are different from each other? Okay, so you are saying that angular diameter distance and luminosity distance. So they are defined means there are two ways you can measure the distance. In one case, you measure the distance through the flux that you receive from the how bright an object. Okay, let's say supernova, right? And you measure the brightness of a supernova, right? And measuring that brightness, you can measure the distance as the standard with this relation, these techniques. That I can always have this apparent luminosity, the actual luminosity by the area, right? And the other case, if I have some standard ruler in the sky, if I have some kind of rule, some kind of specific distance in the sky, okay, that I know of, right? Then I can see, I can look at this and I see that what angular separation it actually subtends at the present location. What is the angular separation of that distance at the present location? I can measure that angle. Okay, and by that way I can measure, I can define a distance. Right? So they measure the things in a two different ways. Right? One, they measure the distance to how bright an object is, and another case they measure the distance. What is the angular separation of a length? Okay, in the sky. If I have a length in the sky, what is the angular separation? Right? So there are two different way measurements. That's why they are means obviously their relations or their the way the expressions are different. But again, as long as we know that, because both things take care of the fact that there is some amount of light is coming from that object to you. Okay, and if you assume that in between there is no, I mean that the photon doesn't get lost, doesn't get absorbed, and whatever, so everything is given intact, right? Then I mean, like even if they are two different ways, their expressions are different, but they have a relation. Okay, so in a sense, if I know dA, I know dL. At any redshift, if I know what is the angular diameter distance for a given cosmological model, I also know what is the luminosity distance at that redshift, or vice versa. If I know the luminosity distance, I can know the angular diameter distance at that redshift. So there are two different ways of measuring distances. Okay, but
the measurement and calculation is okay.
Your sound is completely distorted. I cannot. Hello?
Define that, but
your sound is completely distorted.
I said that the mathematics is okay.
No.
I meant to know that.
Okay. I understand. So these are not. So the actual distance that we call is the physical distance. This is the actual distance. Okay. This is what is called sometimes called the. If I don't multiply this by the scale factor, so this is the moving distance. If I multiply this by the scale factor, okay, this is called a physical distance. This is the actual physical distance, right? But I cannot measure this. There is not a direct way I can measure this actually the physical distance. So this physical distance is always the same. This is the physical distance. That you say that okay.
Okay, sir. So then, sir, from either way, either by
I measure this physical distance. Either way, I measure the physical distance. One I measure to the angular diameter distance. So this is related to the physical distance by physical distance into 1 plus z. In the other case, I measure it through the angular diameter distance, okay, which is the physical distance divided by a 1 plus z.
Okay,
but
sir.
This part is always the same. All the cosmological information about the universe is there in the physical distance, right? Okay. So this is a two-way of measuring the physical.
Okay, sir. Sir, is there any other methods?
Yes, one through the angle and one through the brightness. Okay, and those two are basically related to that. Okay, so as you can see, the unit is always distance. This is a unit of distance. This is a dimensionless quantity. Fine. So this is a unit of distance, and this is your physical distance.
Yes, sir.
Hello.
Yes, sir.
Okay. Is it okay?
Sir, is there any other?
Your voice is completely distorted.
Yes. Okay, sir. Sorry for that.
Yeah,
I meant to say that, sir, And there sir any other methods to determine the distance?
So these are the mostly the two things that we measure the distance, fine. There can be other measurement like volume measurement or other things, fine. Or then we can go for the nonlinear in the structure like linear scale, the fluctuation, those things. But mostly the distances that we use to get the cosmological information is mostly depending upon these two distances. One is the luminosity distance. I use mostly the supernova, this kind of thing for that measurement. Or there are some standard candles, so I use those things. Or I use the angular diameter distance, where I use the CMB, or I use the baryon acoustic oscillation to use the angular diameter distance. Okay. So, but mostly these are the two distances that we use in cosmology. One through angle, one through brightness.
Okay, sir. Understood, sir. Thank you, sir.
Okay. Any other question? Anybody?
Sir, I have a question. When we are trying to infer the density parameter for the curvature from the constraint equation, we are implicitly assuming that there exists no other species than matter, radiation, and dark energy. How much justified is this assumption?
Okay, so what you actually see, so let's go to this expression. Okay, so here, so this is pretty much, so what we assume is that in the universe, there is whatever we have, there is some non-relativistic component. Okay, now in the non-relativistic component, we can have whatever we see like baryons, and this also consists of dark matter. So this also has the dark matter, so this can have baryons. Okay, all those light emitting particles, which all know the standard model things or whatever, right? The stars, galaxies, hot gases, everything. Plus, it can also have dark matter. And as I said, we still don't know what is this dark matter. There is also a lot of unknown things about this dark matter, right? We don't know. But all those things we termed as a non-relativistic because we believe that because mostly dark matter means cold dark matter. So we assume that these are very cold, their temperature is very, very small, so their kinetic energy is very small compared to the rest energy. Okay. There are also models like warm dark matter model, which one can actually sort of incorporate. There can be model like fuzzy dark matter or other things. But for the timing, what we actually assume that all those non-relativistic components that we have, which can be baryons, which can be dark matter, that we have in the matter. Then we can have relativistic component. Now I said that the most of the relativistic component coming from the CMB photon. That is the majority. That is the maximum contribution. But there can be other non-relativistic particle. Maybe if there is some massless neutrino or any other, you can think of some exotic particle that is coming from some particle physics model. You feel that they are relativistic. Okay, that is there. But I am not saying what is there. I am saying that all the relativistic data that we have in the universe, right, they are here. Okay, and the rest is dark energy. Now, here I put a very specific dark energy model, which is lambda, where equation of state is -1. But there you can have many more things. There you can have, I mean, more like kind of scalar fields or other kind of particles coming from modified gravity or other things. That maybe we can have. That we can discuss in our dark energy. But this takes care of all the dark energy. For the timing, to make life simple, we assume that a dark energy that has a W equal to -1. And this is curvature. So whatever you have, so I can just categorize them, all these non-relativistic, which are moving much smaller than the rest energy, that I put over here. Whatever moving around means they are radiation, fine, they are relativistic, they are moving kind of comparable to the speed of light, they are here. Okay, there are some dark energy, but for the time being, we are putting dark energy is very specific, cosmological constant. So then you can say that we have sort of considered all those things. Now there can be unknown thing among here, like dark matter. I don't know what is the dark matter, what kind of dark matter. There may be some more non-relativistic, some relativistic particles, some extra relativistic species are there. People are considered, right? Maybe more than photon or massless neutrino. There may be some extra relativistic species, fine. That is there. That is already there. But effectively, when I use the background relation, I can all plug them behaving like P equal to 130. There may be more dark energy, exotic dark energy component, where W is not -1, but some other behavior. So those can be incorporated over. Fine. But otherwise, whatever we have, we can actually broadly classify it, at least at the background level, by these three components.
Okay. Okay, sir.
The
So when we use omega m, we take W as 0, and for radiation is 1/3, and for dark matter.
For dark energy, for the timing we take -1, but these can be can vary. This can be
right, but that can vary only in a certain small range.
That means you can make model where it can have large variation, but then with observation we can actually make that how far it can vary.
Right. Right. So here's my question. What if there's some material which has W, let's say, I don't know, 4/3? I mean, this might be a silly question, but I'm just asking, how do we...
Now you can see that you can have, I mean, like just convince yourself. So I said that P equal to W that I wrote, fine. Now with W equal to 1, so your P is equal to rho. So this sometimes we call it a stiff fluid, fine. Okay, where the rest energy is roughly same as the kinetic energy, fine. Now, if I have W greater than 1, then your velocity has to cross the velocity of light. So that is not possible.
Okay, right. I see.
Okay.
Okay, thank you, sir.
Any other question?
Sir, I have a question. I'm doing this very time is very limited. So my question is that you have discussed about the matter radiation equality, but now we know that it is the matter dominated era. But from that matter dominated era shifting to the dark energy dominated era, there is a chance of this type of equality. That means
that I wrote, fine. I just wrote you, fine, here where it goes. Yeah, so I can have, so what we have? So here I have a
lambda equals to omega.
Yeah, so depending upon what kind of value you have, let's say we have around, this is 0.3, around 0.7, so around 3/7, fine, roughly. So this is around what? Around 0.4, something like that, and to the power 1/3. So I can get an era when it goes from matter to dark energy. So what you have actually, if I draw log scale, log rho versus, let's say, log t. So I have, or rather log A, let's say. Okay, A goes like t to the power half, A goes as 1/3, sorry, t to the power 2/3 or something, fine. Okay, let's write down what I have. So I have A goes as a to the power -3, rho m, rho r goes as a to the power -4, rho lambda is a constant. So if I draw log scale, fine, so log A versus log rho. So log radiation goes like this way. Okay, so let's say this is radiation. Then as you can see, the matter actually goes a little slower like that. Okay, so this is matter. Okay, and dark energy just remains constant like here. Okay, so this is basically your A equality, and this is roughly your when A lambda. So very early time radiation dominates, matter is subdominant. Then after A equality, matter starts dominating, radiation falls, but all through dark energy is quietly sitting over here. But as because this is constant and all these two are actually sort of diluting, so at some point dark energy will start dominating. Okay, and that is happening around sometimes very recent. Okay, very recent past. So that is what is actually happening.
Thank you very much. So can I ask one again a question about non-technical question?
Sure.
Sir, it's a non-technical question because I'm very much interested in dark energy. So in future, there is any chance for a hardcore theoretical research in dark energy?
So we'll discuss it when you do the dark energy. Okay. So
okay.
Just wait till the dark energy. Fine.
Thank you, sir.
Okay. Any other question? Okay, so I stop over here. So I just, Manavendra, you can take over and just go through the students. You can go through whatever the link he said in the Google Colab, and you can just see what we'll do. Whatever we have discussed over here, all these angular diameter distance, luminosity distance, age of the universe, you will actually see for different combination of omega m and omega radiation, omega lambda, how they actually behave. Right? So I'm just stop sharing now. I'm just stop, and you just go to the Google Colab and do that, fine, and Manavendra will help, fine. Okay, Manavendra, you can just do it, fine.
Hello.
Yeah, you can take over. Okay.
I'm audible.
Yeah, you are audible. Yeah.
Okay, so now I'll share my screen.
Yeah. That's great.
Okay. So you guys can see my screen. Hello.
Yes,
Yes.
sir.
Yeah. So everyone has this copy of this IPython notebook.
Yes, we have.
You have provided the notebook.
Yeah. So I request you to go to Google Colab and open this notebook there. So if you have any trouble, you know, opening it, let me know. So, okay. So everyone ready? So I'll start now. So the core idea is just give you a,
So how to open the file in Google?
Okay, so you have it on your desktop or on your, drive?
So we have downloaded it. So we have it in our desktop.
Oh, so what you can do is you open, search on Google Colab, open the website, and then, okay, I'll just show you how to do it maybe. Yeah. So you just see my screen. So basically I'll Google Colab and open this site. And then this thing will pop up, and then you can see there's an upload button. So when you click it, it will ask you to choose file. You choose it from your desktop or your drive if you have it there. Okay. Okay, that should do it. So I'll now switch over to my own notebook. So yeah. So if anyone is having trouble opening it, let me know. You should have a page something like this once you open it. Okay, so I think I'll start going over the notebook, and the aim is not to go into the very details, but just give you a taste on how some quick calculation. Okay, so someone is asking me to repeat the process, so I'll repeat it once more. Please pay attention. So just Google Colab. Click on this link which pops up, welcome to Collaboratory. And this thing will come up. You select on upload. So you can see my cursor, it's on the upload.
This thing is not coming up for my Colab in desktop.
Are you logged into Google account?
Yes, sir.
Sir, can I say something?
Yeah.
Sir, we can open from that file and open new notebook and get that page, that pop-up window.
No, so if you have like you have to go to the Colab website and you can just upload it.
I think after that
he
is not finding.
Sorry.
Sir, I am saying that first 20 tasks, just that he's not getting that pop-up window. It can be get from that file and then go to the open a notebook, and from that you can upload.
See, for that actually you have to reach the Colab website, and
right. After that.
Yeah, so you can do this thing as well.
Yes, you're right. I have found it now.
So there is a file option. There is an open notebook option. You click it and you can get this window. Okay. So everyone fine with this now?
Yes, sir. Now, sir, which file to upload?
So you should have downloaded a file now. This file called copy of Friedman.ipnb. This I sent you the link to a Google Drive folder.
Yes.
Yeah. So this particular file you have to open. Okay. In case you have it on your drive, you can just open with Google Colab. So we are short on time, so I'll be very quick. And the idea is to just show you that how some simple calculation can be quickly done. So, basically, as you have seen in the lecture, for doing the cosmology at the level of backgrounds. Background means when we assume the uh, uh, that the space is homogeneous and isotropic. That in that case, you can see we can reduce the general metric to FRW class of metric. Now we'll be working with this metric, and when you have this metric, the only thing you need to do is solve some integrals and solve some ordinary differential equations. So if you know how to solve ordinary differential equations, you're good to go. What we will do here is actually we will use, so we don't want to write an algorithm from the scratch. So what we'll do, we will use the integrators from this Python package called scipy.integrate. So the first actually cell actually imports those things. So scipy integrate, we import two. We import two basically packages. One is ODE which is as the name suggests, it is for solving ordinary differential equations. Then there is a package called quad for just doing integration, and ODE is another package for doing the solving ordinary differential equation. So we just run this thing, we get the sum. Yeah, so this imports the packages. Then this is basically the details. This you must be familiar from your lectures. Now the main equation which we have to solve for is this Friedman equations. Now you can, as you have seen, it can take, you can write it in two particular form, the second order equation and the first order equation. First order equation, you can try to solve the first order equation, or you can try to solve the second order equation. It's equivalent. But the one thing I should point out when solving this first order equation, what happens is if you have a cosmology in which your universe is expanding and then falling on itself, contracting, then what happens is a dot by a square, it increases with time. There comes a moment when this goes to 0 and then it reverses back direction. Now when solving this first order equation, there can be a numerical issue that can arise, that around that 0 point when the a dot by a goes to 0, what can happen is your numerical integrator or whatever ODE solver you can use, it can show that this particular thing on the right is close to 0, and it can be taken as to be very small negative values. In that case, your square root of this particular quantity can become imaginary. So your numerical integrator will break down. So that is a word of caution if you're solving this equation. So solving anyway second order differential equation is it's quite general actually, and it's really helpful. But here we'll just use this particular equation for simplicity. These are the notations which have been defined in your lecture. Now, if you look at this equation, you have to solve for A. That means you have to solve for this thing, and plus you have to solve for this source terms, rho d, and kappa terms actually. So kappa terms evolves at this kappa c square by a square, so no issue here. But we need to know how this rho evolve. So how rho evolves depends on what is the fluid you are considering, what is the model of your rho is there. For example, if you consider a pressure-led dark matter, it just goes as 1 by a cube. In general, if you have a fluid with equation of state W, so W is basically the ratio of pressure to energy density, and if you know W, then you can calculate the evolution of rho as in terms of this integral. So you have to solve for this integral, and then you can get. So let's, if you quickly see, if W is, for example, say a fixed value, then this integral reduces to log of 1g, and exponential of log is actually just the same quantity, and then you get whatever is this 1 plus g W is to the power 3 basically. So 1 plus g to the power 3, and then W is there actually. So this can be readily integrated for W equal to constant. Okay, so basically you have to solve this, substitute it in this equation and solve for this. This is what we are going to do. Some notation, J redshift is defined as this particular quantity. A naught we will take equal to 1 throughout this lecture. And A, so 1 plus G is actually inversely proportional to A. So here we consider a universe, just for the demonstration purpose, we consider a universe which has just cold dark matter. In that case, all these terms are ignored, and we have just this particular term. and you can write the whole differential equation in terms of this particular quantity, and this can be readily integrated, and one can get this particular solution. So one exercise which you should do is actually do this integration and do this integration for different value of constant w. That is helpful actually, and also write h as a function of z. That is simple exercise, just you can do with pen and paper. Now we'll have some codes on how to calculate A of t if someone specifies me W of g for dark energy and present density parameters. So in this particular code snippets of codes, what we'll assume, we have a universe where we have only dark matter, dark energy, and possibility of a curvature term. In that case, we know dark matter is pressureless, so W for dark matter is 0. W for G is actually a model for dark energy. So for different models of dark energy, energy will have different W of G. So we want to have a formalism where we plug in W of G, the functional form, and we get the solution for A of T. So this code basically does that only. So here we define a function which basically returns the value of W as a function of G. Just for the sake of simplicity, I'm just returning a constant value of minus 1.0, which is just equal to what the value of W which we have for cosmological constant. And then actually we define a term dA by dt. So dA by dt can be just obtained from this equation. So remember, we have rho dm, rho de. We are ignoring all these terms, and we have this kappa c square by a square term. So using this equation, we write this equation in this particular code, and then also we have to know how dark energy works. So once we have W of G for dark energy, remember we have to do this integration. So whatever integration we have in power here, power of exponential, we write it in this function, integrand integration W function. So this function basically, this is the function that is in the power there, and then this function integrates that function, and we use this here, and then we make the substitution in the Friedman equation, and we get d of dt. We pass this d of dt to a function which is called OD int. It takes dA by dt, initial condition, and the time series which you have to solve for. And then it takes the two arguments, omega dark matter, omega dark energy, and then it gives you a solution for this particular thing. And this function basically plots it. So, okay, so this is just an overview of this function. How to use this OD int function for this, we don't have time to go into details, but I suggest you Google it up and you later see how what is the format to use. So there's a so we have nice references on the internet. Once you Google it up, sci-fi references are also there. So those are really clear. Once you go through it, do some simple example, you can get a hang of this. The idea is we have to solve this particular simple equation where we are solving this A dot by A. You can write basically a C code or Python code or MATLAB code, whatever code you want, and you have to solve for this equation. Okay. Okay. Is there a question? Okay. No. Okay. So then this function basically plots this function. So I have just plotted it. So I'll just plot it for, so I have 0.3, suppose dark matter is in the, and I set it to 0.7, I run it. So I get something like this, which is accelerating universe, which is universe grows with time, and then when dark energy dominates, it accelerates with time. So you can basically play around these functions, improve it. It's a very rough piece of code, but you can define it and you can use other solvers as well. But yeah, so this is it. So then how to calculate the age of universe? So the universe where we have only dark matter, that is called Einstein de-Sitter universe, or just EDS universe. So there what you have is actually we found the solution for Einstein de-Sitter, which is basically this particular solution. Now what you can do is, this is a function of A as a function of time. So either using substitution or by just doing some integration, what you can show is actually age of the universe comes out to be 2 by 3 h inverse, h naught inverse. So once you measure the value of h naught, you can predict the value of age. So I'll put h naught in a units which make it more clear. So what normally do is you write h naught as is terms of this dimensionless number called h, and whatever literature you read or whatever experiments of the cosmology people do, they quote this dimensionless number, whether it is 0.5, 0.6, and you put that in this and get the unit full h naught. So just to give an idea what this number is, h naught is actually equal to h by 9.7 billion years. So if I take the data current value or agreed upon value of h, that is point upon 0.7, this comes from the observation, and I substitute it into this formula, I get age of universe roughly 9 billion years. So this is a bit contradictory, because in our universe you can observe objects or the astrophysical entities which are older than 9 billion years. So then actually what happens is, if you incorporate dark energy calculations and you have an expanding universe, this number increases and it goes to roughly around say 13 billion years. So here is one exercise. So what you do is you assume omega k equal to 0, and then you plot the age of the universe as a function of present day dark matter contribution. So what happens when you take omega k equal to 0, and we assume that we only have dark energy and dark matter. So in that case, we have this term, and omega k we are assuming to 0. Then basically omega not for dark matter and omega not for dark energy. Those are two parameters which you have to constrain, and the sum of them, their sum has to be equal to 1, because we have assumed curvature to be 0. So in that case, actually, what you need to do is you have to do this integration, and then you can actually find the age of the universe given a particular value of omega dark matter, omega dark energy. The following code what you actually does the same. So first I define a function called 1 by e1 plus g. So which is basically this function e1 by e into 1 plus g, and then I integrate this using quad. And this integration actually gives me age in terms of h naught basically, and h naught you have. So you need to plug in your value of h and you get your result in terms of billion years. So for example, if I have this code and I put the current best fit values, which are 0.3 for dark matter and 0.7 for dark energy, and I run this piece of code, I get this 0.96. So you actually substitute this value. So this is in terms of h naught, and you substitute the value of h naught and you'll get something around 13 billion years. So which is the currently constrained age of the universe, which is actually what data suggests is age of the universe is. Then next thing is distances in cosmology. So what happens, all the observations which we do most of the observations are just in terms of electromagnetic signals or radiations or photons which we get. But we need to interpret the information that is coming from those photons, and for that actually there are different kind of distances that we have discussed in the lecture. So basically for each astrophysical event, we have a marker of time called z shift, and then we have a co-moving coordinate marker as well. The idea is that light signals, they travel on a special path, and that special path is called null geodesics. So given a particular z shift and the signal which you are receiving at say z shift of 0, you can associate a coordinate with that particular z shift, and that associated coordinate is this RC, which is defined in terms of this particular quantity, and which again involves an integral which is called capital I, which I'm calling, and this again is an integration over e into z. Okay, and this e into z, if you remember from the previous material, it is defined as this particular quantity. So how your E evolves depends on how much dark energy you have, how much curvature you have, how much matter you have. So basically E depends on your cosmological model. So your distances depend on the cosmological models. So once you have once you observe electromagnetic signals, and you know how much light or intensity you are getting, and once you can also separately observe redshift, you can connect the redshift and the distances, and those are connected by cosmology. So you see redshift and the distances, they are connected by a cosmological model, and you observe redshift and distances, and hence you infer information about your cosmological model. That's the way you do cosmology. So there are various distances defined. There's angular diameter distance, which often goes into observation. I'll not go into details what is the physical significance, and then you have luminosity distances. Now I'll briefly comment about the luminosity distance. So luminosity distance is basically related to if you know how much energy a particular supernova is emitting, and you know independently the redshift, then given the energy that supernova is emitting and given the energy which you observe at your devices or your detector, you can infer the distance actually. And if you independently know the redshift of that supernova, you can get a relationship between distance and Z. And then you put your models and try to compare it with the theoretical prediction. So what supernova observations actually give is this quantity called mu. Now mu is dependent on this luminosity distance. Now trace back that this luminosity distance is dependent on RC and redshift, and this RC is actually dependent on your cosmological model through this I. Okay, so once you have a relation, once you observe mu and you know Z, then you can plot mu as a function of Z, and you have similar curves for your theoretical model, and then actually you can constrain your parameters of cosmology or cosmological models. There is another important parameter called deceleration parameter, which is defined as in terms of derivative of A actually. This is the definition of derivative, and at present actually present value of Q naught can be written as in terms of this summation, and it actually the value of this Q naught depends upon again on if you have dark energy, what kind of dark energy you have, what kind of equation of the state you have, and this Q naught can be measured for very small redshift. So in a very small redshift regime, DL can be extrapolated in this particular relationship. Now DH here is basically a constant which is defined as, so I must have, yeah. So DH is basically called Hubble length, which is defined in terms of C by H naught. So everything we plot in terms of DH. And again, DH, since DH involves Hubble constant, so you need to measure your value of small h in order to get the real number, what is the unit full number of DL. So this basically function actually calculates your RC, and then plus it also calculates your other functions. Just a moment, give me 1 minute. I have to plug in my desktop. Yeah. Okay. So again, there is a function for calculating 1 by E, and then there is a function for integrating that to get I. So I is defined in terms of this integral. And then you have a function which calculates RC depending upon what the curvature is. So remember the RC has this particular relationship. So it's a conditional relationship in what regime, what is the volume, what will be the form of RC.
Sir,
And yeah, please.
what is DH?
So DH I defined. Basically, it's a constant which is composed of two constants called C and present value of Hubble parameter. So C by H naught. Okay. So these are the constant basically. So H naught you constrain from the observations, and C is, is the speed of light. So it is constrained from many different things. Okay. So basically all the distances we write in terms of DH. Okay. And to have some idea of what is the scale of DH, what you can do, you can substitute value of C, and then you can also substitute the value of H naught and get numbers, your result in terms of megaparsec, kilometers, meters, whatever you want. Okay.
Okay,
so then you have this there's a small piece of code. Basically what then shows is how to calculate DL and how to calculate DE. So for example, calculating DL actually we need to calculate R as we need to calculate DL as a function of redshift. For that we need to calculate RC as a function of redshift, and for calculating RC we have to do this integral and substitute it in this formula, and then substitute that RC here and get mu out of it, and then we get mu versus Z relationship, which is actually which you can compare with supernova data, and then say something about your cosmology, whether dark energy is there, it should not be there, what is the model of dark energy. All of those things can do using supernova data. So supernova data is one of the observations. There are different other type of observations. Maybe those will be covered in your lectures on dark energy. Okay. So this is a small code which basically uses these functions to calculate different quantities as a function of Z and then plots them. So here's one plots. Basically it plots distance. What do you say? It plots basically angular diameter distance as a function of Z, and again we use the unit of DH. So this is just the function. I'm calling that function. Now, for your last part, actually, what I'm so I have also supplied you file called jla-mube.txt. Now what you can do is upload that file here. Okay, so I'll show you how to upload that file. So you can see there is this file symbol here. You go click it, and then there is an upload button. I have already uploaded it, but you can just click it and select the file. For example, I'll select this and upload it. It's already there, so I won't upload now. Yeah, so that you can do. Okay, so let's briefly run this code. Then run this code. Okay, and then let's load this data. This loads the data, and basically then what I do is I use the so as we have seen, I have written a code for calculating luminosity distance, and then I use those functions to calculate the luminosity distance for different combination of what you say dark energy and dark matter ratios, and I run this code. It plots me this curve. Now what you see is there is a mu versus z relationship. Now let me again remind you what mu was. So mu is actually a function of dl. Now remember, dl is a function of z shift z, and again it is calculated to theory where this particular integral and rc. So yeah, so rc we calculate this dl from theory as well, and then we calculate mu from this, and we take the mu from the data, and we do this plot. Now you can see the red line is the observed line, and then the model in which you have say only dark matter, that is so basically the two numbers quoted here. First is for dark matter percentage component, how much proportion of dark matter is there of the total density, and second is number is for dark energy. So the model which has like say only dark matter, no dark energy, it's a bit far away from this red line in comparison to the model in which you have 0.3 proportion of dark matter and 0.7 times 0.7 70% of dark energy. So this such kind of curves were used in a more sophisticated analysis using the data from supernova in late 1990s. And then there were groups, particularly two groups, Perlmutter and Rees, who used supernova data to make such curves, of course, along with all the sophisticated data analysis. And they found that there has to be the universe which we live in has to have dark energy, and this dark energy is dominating over the dark matter content. So this is just a taste of what you can do with these simple calculations. Of course, if you want to do a full-blown supernova data analysis, you have to look into the papers, and actually they provide you what they provide is they provide you details of their errors of their observation. They provide you covariance matrices and everything for their observations, and then you have to do, you can either use chi-square analysis or what do you say, Bayesian analysis. I think that will be covered in later parts when dark energy and data analysis will be covered. So, but this is just to give you a hint. From these simple calculation, actually you can show that we need dark energy. There has to be something with a negative equation of a state. So this is just simple, demo. Now then there I have put up an exercise. It says you assume curvature is 0 and you have dark matter and lambda are only component, and then you find the best fit value of lambda matter and lambda dark energy provided the mu data points which you have. So this is a simplistic code which tries to show you give you some basically hint. It's a very simplistic demonstration, but you normally what you do, you again do such kind of numerical experiment where you have a model and set of differential equations, and then you have set of parameters, say the amount of dark matter you have, the amount of dark energy you have, and then you put what you can do, you can put a loop over a set of allowed value of dark matter. For example, say here I'm putting a loop in a allowed value of dark matter which is like say 10% to 100% in the steps of 0.1 in steps of 10%. And then what I'm doing, I'm taking the difference of mu data and mu theory, and I'm just plotting this. So you see there's a bump around here 0.2. Now again, this is a very rough calculation. So you are getting a prediction which says you have like 20% of dark matter and 80% of dark energy, but actual value is actually 0.3 and 0.7. So that is some kind of hint. So what I will suggest is you actually do these simplistic exercises and try to calculate age of the universe as a function of different dark energy parameters. Try to, if you are very enthusiastic, you might try to take some supernova data from early on papers and try to do that actually. But this is just a demonstration how to do solve the background cosmology. Okay, so this is the basic demo. You have the notebooks with you. You can play around with this. And I'll put one word of caution here. The integrators which I have used are inbuilt integrators. Now they might now, and the equations which are you solving are kind of are nonlinear. And at some moment, those integrators might break down depending upon how much the spacing of dz you have. So for example, when I'm plotting this last curve, you see basically you see some error popping up. So this error is actually when doing the integration for the initial points, actually you don't have enough points to sufficiently sample your jet to do a good estimate of integration, and you have some errors basically. So whatever, if you are doing really sophisticated analysis, you should be aware what integrator you are using, and you should be aware of how it is affected by the spacing in dz or d time or dA which you are taking. Okay, so and if you are familiar with any programming language, say for example Python, C++, Java, or whatever you use, it's an illustrative exercise to actually solve these equations with different set of parameters. So I think that is from my side, and I think we are way over the time. So if you have a question, please.
Sir, can you explain that GLA data, what is all about it?
So basically what I have just put in is this analysis, this curve actually I have put without any error bars on it. So this is basically, I have just copied the data from their website wherever it is available. And I have just made a list of mu versus z without any error bars actually. And then what I have done, I have calculated mu from my our theoretical calculation. So basically I have calculated mu using by solving these equations. Now remember, this gives me a dot as a function of time or z shift, and then basically this gives me e square. Now you remember this e, the integration of this e actually is this I, and this I actually goes in this RC, and this RC goes into the CL. So basically, depending upon your cosmological model, your z shift versus luminosity distance relationship will change. And this mu is totally dependent on luminosity. So you can just, instead of saying luminosity distance relationship, you have this mu distance relationship. And that is what we have calculated from our model. And that is, and we have also taken it from, I just copied this supernova data of redshift versus this mu and plotted all of this together. That is what I had done.
Okay, sir. And second one, that is covariant matrix data.
So basically, normally what you have is when you have a number of data points, actually, the whatever experimenter or whatever observation team is there, they will also give you a set of error parameters, how much confidence they have in their data. So then actually a full-blown analysis is done by writing considering your errors in your data as well. So in the considering errors, then you don't say that this is my best model. You say only that I have this particular probability for this model to for being the true model. So given the probability of the errors, how the errors are distributed, you just make a probabilistic comment in the end that given these are the errors, I can say with this much confidence or this much probability that this is my my universe has dark energy or not. What is the proportion of dark energy I have? So that is a detail that should be covered in a separate lecture because that is really involved actually. So I think this workshop is all about data analysis. So I think we'll go into details a lot in later lectures. This is just for demonstrating the purpose that how using just the basic equation, you can show that we need dark energy just with using some simple data. Yeah.
Okay, sir. Thank you.
Guys, if you have a question, please pop up.
Hello, sir. I have a very fundamental question. In the exercise 1, you have defined omega z, the dark energy US parameter, to be equal to -1. And you have calculated the scale factor, the expression for AT. So if we want to consider some other kind of matter composition, then we have to just change this omega z value, and then we can calculate them.
Yeah. So basically, for a different type of Zo, you have different type of W, and you can make the substitution and calculate it. For example, you can see this commented line here. They have commented two lines of code. So this is actually there is a particular parameterized model of dark energy called Cpl model. So this particular W of G is an example of a dark energy model. So when you have different type of dark energy models, they will have different type of Z. W of Z. So at the background level, what you only need is just W of Z. So at this background cosmology level, I'm working under the assumption of homogeneity and isotropy. All you need from your dark energy model is to say what your W of Z is, and then you can calculate the other quantities. For example, luminosity distance, redshift relationship, how the universe expand, whether it will collapse or keep on expanding, all these things.
Okay, thank you.
So what I will encourage is actually to take this Python notebook just as a starting point, and then try to refine it on your own. You can take the help of the people who have experience in Python, or you can even ask me question, etc. You can mail me later if you have any particular need. I'll float my email ID. But I suggest if you are experienced with any programming language, whatever is your native programming languages, you go ahead and do it. Even if you don't have any experience with, say, particular programming language, you just learning Python is not so tough. You can just go do some online classes 1 or 2 days, and then you can just use the packages. So that is the starting point. To use the inbuilt packages, you can even use the MATLAB and Mathematica. They also have inbuilt integrators. So but just try to do some exercises. That would be helpful. Yeah. So we have any other question?
Okay, so if we have no other questions, then let's thank Professor Anjan Sen and Manavendra for the nice talk and the hands-on session. So I also have some announcements. So there will be no class tomorrow. And also the students who are joining, please try to keep your microphones muted because sometimes noises are coming. And also if you think that your voice is breaking, then just type your questions in the chat box so that we can read it out. Okay, thanks. So let's meet day after tomorrow.